What were the strengths of this paper?
It's really easy to read. It's really structural, and I like that. They have like the titles, subtitles, and the graphs are easy to follow.
Yeah, so the organization is really nice. I completely agree. Other strengths?
I think thoroughness. They covered a lot of systems, like just in the variety of like all the systems they looked at, both terrestrial and aquatic. And then within like each of those, like there's a lot of like differences in like the biomes covered too. So I thought that was really cool. It's a really holistic approach.
I like how they connected it to like so many different things. Like they talked about disease and like things that you wouldn't even think of that would be affected by apex predators. And like they acknowledged that apex predators weren't the only aspect that was affecting it, but I thought that was cool that it was so widespread.
Sorry. The other one was I really liked how they acknowledged that even with all these predictive models, they weren't really able to accurately predict exactly what was going to happen because of the complexity of the trophic nature of all these different systems. It was really
Yeah, absolutely.
That was crazy, like, one species could, like, change the entire biome. Like, could switch from, like, a grassland to, like, a tundra.
Right. What about weaknesses of the paper?
A lot of their data seemed like anecdotal.
Mm-hmm.
Like they just like told this one story that didn't really say how it like fit with a lot of other things.
Fair enough.
I thought that was kind of excusable because they did cite like everything, and it is a review. So like they kind of point you to where you can find the hard data. But they're just kind of reporting the general results, so that didn't bother me as much in this one. I know the paper was focused on like the importance of top-down interactions.
Mm-hmm.
So this like comment might not be relevant, but they only mention like bottom-up forces like once.
Yeah.
At the very end of the paper, and they just say that they're ubiquitous and fundamental, and they're necessary, but they're not sufficient. And I would have liked to know more behind what made them say that. I mean, obviously, I know the focus of the paper is on top-down. So
Right. No, I
but,
think
like,
that's a really good point. They don't talk
like,
about
why they prioritize it.
Mm-hmm.
I think would have been good.
I think maybe you could construct some kind of a model with trying to like simulate all the different levels and then how they affect each other and see if you can find like the threshold where that like a certain level of consumer absence leads to the collapse of all the other interactions.
Right.
Also, like, I think it's interesting that there's no good or bad in ecology. Like, animals just do their thing. Like,
Yeah.
we put good and bad on stuff, but just because a system is altered, that doesn't necessarily mean it's bad.
Yeah, so let's talk about that philosophically. Like, how would we define good, positive impacts?
I think there's a certain bias in conservation, particularly of thinking like the ideal is always like a historic one, but that may or may not necessarily be true. Especially like with the impact of like the widespread impacts of like humans lately. Like I think there's this like divorce of thinking like there's wilderness and there's humans, but in reality it's a lot more integrated. And especially as time has been, like populations are growing and whatnot. So I think to some extent that's like a paradigm shift that I think we kind of need to take on too, is looking at like, okay, well, this is the reality of the systems we're working in. How do we work within that? Not necessarily just like, how do we get things back to like pre-colonization?
So like, how do we reach out to those people that aren't motivated by cute, cuddly animals and don't necessarily have a large scientific background?
Epidemics in terms of treatment and like work hours lost and things like that, and like property damage from wildfires and impacts on agricultural production and food resources.
Trying to talk to somebody in the Midwest, right, and they're a farmer, for example, talking to them about their crops and how that might be affected by some of these, issues is one way to actually get them to listen. Particularly if you can try to present them a practical alternative that is good for their pocket, but also good for the environment. Right. And the reason I picked this paper to be sort of the culmination paper, not because it's depressing, of course, but because I think it does a great job of connecting everything from biogeochemistry up to food webs to, it just is all the things that we've talked about in various different ecosystems on planet Earth, even terrestrial ones. And so I think it gives you a whole big picture idea of how important species are.
You want to think about this as a scientist, right? If we're trying to go out to a lake and we want to know the species diversity of the fish there, right? We're going to fish a lot, maybe we're going to employ different methods. Maybe you fish with your rod and reel. Maybe you go out there and you deploy some sort of bite nets or something, and you're going to try to get the best idea of who's actually there, who actually lives in that lake. Well, it turns out that sampling can be pretty hard to actually estimate this accurately in real life in nature, right? And so what we do is we use the laws of probability and statistics to actually inform the way we classify this. So we tend to use two different techniques. One of them is called a richness estimator, and the other one is what we call collector's curves or rarefaction curves. And we're essentially using that to evaluate how good our sample is.
How did they decide basically where the buck stops for like one sample, once, twice?
Right. No, and that's a fantastic question. This was formed after doing lots of mathematical and theoretical sampling, and there are other techniques to do this. So this isn't the only one. So different schools of thought for how we might calculate this. This is actually just one example. But good question. Yeah, it does seem maybe slightly arbitrary. Why don't we talk about 3 individuals? Well, it's just because they've done some tests to mathematically look at the probability of which one of these rare species matter, and they think that it happens to be at this level of 2 individuals or less. But we're going to test that and see how good it is with our own data, okay? So what I'd like everyone to do is you're going to go ahead and we're going to create a rarefaction curve, and we're also going to do a Chow estimator for our candy. But what I'd like everyone to do is pretend like you are not, I know people are going to want to pick out their favorite candy. I have plenty of extras, so don't worry about that. But what I'd like you to do is just put your hand in here, pick 4 pieces of candy that your hand just touches first. So like try not to discriminate based off like, oh, I know that's a Starburst. Okay, so pick out the 4, make sure you keep them in order of how you sample them, and then you're gonna come and you're gonna write your individuals up on the board, okay? So you can think of this as we're sampling our lake, right? How many of us are there today? So you can think of this as we're sampling our lake, right? Come up and write your individuals on the board. You're also going to want to know, so you're going to write 2 things. You're going to write the name of your thing. Make sure that you're consistent. Use the candy's color, maybe instead of flavor, if you have different ones. And then you're going to write the cumulative number of species, right? Right, but I want you to do cumulative, so make sure you add them through time. So when you sample 2 individuals, how many species have you found total? Oh, cumulative. Yeah. Oh, okay. Perfect. All right. So we'll just go up there as an individual. And then what I would like to do is once your team writes your numbers up here, I want you to go through and calculate the Chow estimator for your group, right? So there are going to be 12, the first 12 individuals, you're going to have 24, and you guys will have 30, no, I miscounted the number. Oh yeah, 36, that's right. So, does that make sense for everyone? So we'll have a Chow estimator each time, and then we're also going to start and draw ourselves a curve as well.
Are different flavors of things considered different
Yes,
species?
different species.
All right.
Maybe they're the same genus.
All right.
I have an analog for that too. All right, perfect. So you'll be there. So you can come up here and write your Chow estimator as like 1 point, and then you'll make your line for the species. You come up here and add this series, right, for the next 12 points, and then also let us know what your Chow estimator is. Obviously looks a little messier than what happened. You could see how like a computer simulation would kind of smooth that. It seems like it levels off, but in reality there are actually 118 individuals. So we've sampled approximately 33%, let's say a third. And so the actual number of species is 20. So look here, right? The first group, we only found 5 species. So if we stop sampling there, what's our best estimate of it? At what point did that happen? What would you say?
The middle group got closest.
Middle group got closest, right? So if we're gonna, but only with this, right? Only with our child one estimator. So it'd be interesting to see how many more candy we'd have to pull to actually get all 20.